Hey there, and welcome to Raylene Math. Let's take a look at projectile motion. Here we have an object launched on Earth at an initial velocity of 50 meters per second, at an angle of 30 degrees, and from a height of 30 meters. We're told to use g, the acceleration due to gravity on Earth, equal to about 10 meters per second squared. So what is projectile motion? When an object is launched in two dimensions, and is subject only to the force of gravity, no air resistance, no other contact force or jet propulsion packs, then we consider that the object is in free fall but in two dimensions. We call that projectile motion. So the first thing we're going to do is try to model all of this information in terms of the initial vectors, the acceleration, velocity, and position, and we're going to break those down into both x and y components. Then we're going to take each of those 6 components and write equations for them, and then sketch functions for them with respect to time. Now, time is the only thing that all 6 of these components have in common, and so it's really going to be the unifying variable or quantity among all of these things. Okay, let's take a look. We have an acceleration vector, which is going straight down, pointing towards the center of the Earth, and it's got a magnitude of 10 meters per second squared. That means every second, there is a change in the velocity in the vertical component of 10 meters per second. Now we know that the velocity is going, the acceleration is going downwards, so that's going to be a decrease of the velocity. If we want to put the polar components in here, then we can say that the magnitude of the velocity is 10 meters per second squared, and the direction or the angle is 270 degrees. To get the x component of acceleration, we take the magnitude of any vector multiplied by the cosine of the angle, so we get 10 times the cosine of 270 degrees is going to give us 0. Now that makes sense. Looking at the vector, there's no horizontal component. Similarly, all of the magnitude of the velocity has gone into the vertical component, which is given by 10 sine 270 degrees, which is negative 10 meters per second squared. Now these are called the rectangular components, and these rectangular components can be written as coefficients of I hat and j hat. Now, the acceleration is constant. Both the x component and the y component are constants, so their graphs will be horizontal lines. In fact, we can draw those graphs straight away. We will draw them with horizontal lines with a domain restriction, and we'll work out that domain restriction in a moment. The reason we have a domain restriction is because, recall, these are equations for only gravity acting on the object. And if you're launching an object and it's landing on the ground, well, then there's some initial rocket launch force and then some contact normal force when the object lands. So free fall only occurs in between the launching and the landing times. We'll find out what those times are in a moment. But because the acceleration is constant, it doesn't just have these component values at time 0. They're component values of 0 and negative 10 for all time values. So I'm just going to substitute 0 here and negative 10 here. Okay, next we'll take a look at the velocity vector. We are told that the object is initially launched at an angle of 30 degrees with a magnitude of 50 meters per second. So we have an angle of 30 degrees from the horizontal, and we have a magnitude 50 meters per second, and that allows us to come up with the 2 components, the horizontal Vx component and the Vy component. Now we know that Vx is going to be magnitude times the cosine of the angle, which is going to be 50 times square root of 3 over 2, which is going to give us 25 square root 3. These are the rectangular components. I'll put the magnitude and the direction in the angled brackets for the polar components. We're using rectangular brackets for the rectangular components. And so rectangular components just means the base and the height of the right triangle, and the polar components just mean the angle and the magnitude of the vector, which is like the hypotenuse of a right triangle, but it's also the radius of a circle. So that's why we have r for radius, and we have these components when we're dealing with the North Pole and circular motion. Okay, so let's get rid of that circle, and we want to come up with the y component, so we take the magnitude times the sine of 30 degrees, and the sine of 30 degrees is a half. Half of 50 is 25. Now, we see that the x component of acceleration is 0, which means that the x component of velocity does not change. That's because the definition of acceleration is the rate of change of velocity. And if the acceleration is 0, there is no change in velocity. And as a result, we have that the x component of velocity is a constant. And so we can put that in for all times as a constant function 25 root 3. Similarly, for the blue graphs then, the x component of the velocity of 25 root 3 is going to be a constant function from 0 until whenever the landing is. I'm just going to write in these equations here. Ax of t is constantly 0 and ay of t is constantly negative 10. Okay, now working out the y component of the velocity, we see that we have an acceleration of negative 10, which means the acceleration is a constant, non-zero constant, and the velocity graph will be a linear function. The acceleration is the slope, and we're going to have a downward slope or a negative slope of negative 10. The acceleration is the coefficient of time, and then we add the initial y component. So here we're going to have negative 10 from the a component here times t plus the 25. So we're going to get negative 10t plus 25 for the y component of the velocity. That's a decreasing linear function, and we can sketch that, but it's a bit easier to figure that out once we have the time value for the landing. Lastly, we come up with the position equations, and the position is given by 1/2 acceleration times time squared plus the velocity initial times time plus the initial position. Now, if we can forget for a moment that these are vectors and just consider subscripts of x, we can take the x components of each prior rectangular component, and we can take, oh, I didn't put these in here yet, we should probably get that. When we're looking at the object being launched, we have to consider that it is launched from some starting point. We're told that it's launched from a height, these are both in meters by the way, the object is launched from a height of 30 meters, but it doesn't specify at what x coordinate. So basically, wherever you're standing to launch it, make u the y-axis. So we're going to launch from 30 meters above the ground, which means that our initial position vector relative to the origin is a vector of length 30, magnitude 30 meters, and pointing straight up is at an angle of 90 degrees. Furthermore, the x component of that vector is 0 and the y component is 30. So we're going to use all of those pieces of information here to work out the x component of the position vector. So we're going to have 1/2 times the acceleration for x, which is 0, plus the initial velocity for x, which is 25 root 3 multiplied by t, and then plus the initial x component, the initial x position. And so all of that together just gives us a linear equation. We're going to get 0t squared plus 25 root 3 times t, and then plus 0. And so we're going to get the linear equation 25 root 3t. It's a positively sloping line passing through the origin, and so it goes for however long all of the other graphs go on for. We're going to do the same thing, but with the y component equations. So I'm going to pick another color here. There we go. And the y component that we need for each vector is in gray here, circled in gray. And so we're going to take 1/2 of the negative 10 times t squared, which is going to give us negative 5t squared. And then we're going to take the y component of the initial velocity, which is 25, and multiply it by t. And then we're going to take the initial height, which is 30 meters. And so that quadratic equation becomes our vertical position function as a function of time. Now, why these equations have these constant linear and quadratic formats can be discussed in another video called free fall motion, and it's done in the one-dimensional case. Okay, so if we want to come up with that graph, it might be easiest to think about the time domain and the maximum height reached for that parabola, because we have a concave down parabola. Once we get that, we'll fill in this remaining graph. So let's move on to part C, which says, what is the time domain? It's really asking us to solve for time such that something happens, such that the object lands. And the object lands corresponds to only one piece of information, that the height is equal to 0. So when we take our height, which is negative 5t squared plus 25t plus 30 and substitute y equal to 0, we can solve the quadratic equation. So by factoring out the common factor first, and then continuing to factor the quadratic expression, we get that negative 5 multiplied by t minus 6 times t plus 1 equals 0 gives us time roots or time intercepts on the graph of negative 1 or 6. Now negative 1 is over here and 6 is over here. So 6 is the time value that we were looking for in all of these other graphs. We know that that's an open point, but negative 1 is actually prior to the launching time at time 0, so we will not include that for our domain. And the domain of free fall, when the free fall equations are valid, again remember free fall means only gravity is acting. And those time values then are given as an open interval from 0 to 6 seconds. So we can put all of those time values in on the other graphs from 0 to 6. We can put 6 here, and then we can come up with a reasonable graph for the red y component graph. We can also graph the parabola here. So if we finish the red Vy graph, we know that there's an initial Vy velocity or magnitude of or component of velocity of 25, and it's a line decreasing. And if we substitute 6 in for t, we get negative 10 times 6 is negative 60. Negative 60 plus 25 is negative 35. So we're going to start at 25 on the y-axis, or the output axis, and we're going to go down to a height on this graph of negative 35. And then lastly, we went and come up with this remaining green graph for the y component of position. So we're going to take a look at part D, because this is really going to help. The maximum height reached by the object when we have a parabola graph is the y component of the vertex. So to come up with the vertex, we already knew we had the two time intercepts, i.e. time values such that y is 0. And by the axis of symmetry, we can find out where the vertex lies by the midpoint of those values. So the time coordinate of the vertex is the midpoint of negative 1 and 6, which is 5 over 2, and therefore the y-coordinate of the vertex, or the maximum height on this parabola, is going to be the function value, substituting in 5 over 2 for time. You can plug into the expanded function form, or I like to substitute into the factored form, which gave me the time intercepts. And so doing this gives me negative 5 times 5 over 2 minus 12 over 2, which is negative 7 over 2, multiplied by 5 over 2 plus 2 over 2, which is positive 7 over 2. It's no coincidence that we get plus or minus 7 over 2 for each of these factors when we substitute the midpoint of the time intercept values for the vertex into the formula, because that's just showing we have equidistance on either side of the axis of symmetry to these two time intercepts. So continuing to work out the y-coordinate of the vertex, we get negative 5 times negative 49 over 4, which gives us 245 all over 4, and that is measured in meters. So we know that that's the maximum height occurring at the 5 over 2 seconds for time. So taking advantage of that, and taking advantage also of the axis of symmetry, we will get right around here is 3, and right around here is 5 over 2, and that's where the maximum height occurs. And the maximum height of 245 over 4 is 61.25, which is more than double the initial height that the parabola or the object was launched at. And so we get something that looks like that. I'm just going to move this over a little bit to here. Okay, so now we have some sense of our 6 component graphs, and pretty much every question that we will be asked from now on in talks about one of 3 points. I'm going to label these 3 points as the launching point, the point at, or the time at which maximum height occurs, and the landing point. And so we can see A and C for most of these points, or most of these graphs, quite easily. We just have to go in and label point B for the remainder. So if we just take the time value of 3 and a little bit less than that, that's going to give us our b. It might be interesting to label all of the points at point B. So here, for example, we have 5 over 2, comma, 245 over 4. Here we would have 5 over 2 seconds, and we would substitute in 5 over 2 for this equation, and 25 times 5 is 125. So we get 125 root 3 over 2. Here, 3 a little less is 5 over 2, and so we're going to get point B occurs here, and we were going to get 5 over 2, comma, the same constant x component of velocity. Here, if we put 5 over 2 into the equation, negative 10 times 5 over 2, it's going to be negative 50 over 2, which is negative 25, plus 25, which is 0. And so that point seems to be particularly interesting on this graph, whereas the other points don't seem that significant, nor does the point B seem significant on the two blue graphs, because we have constant functions for these three graphs. Okay, so now that we have some more information labeled, let's read the next question. The question asks, what is the horizontal position when the object is at its maximum height? So if we translate this verbally directly, we're asked to solve for x such that y equals y max. Now, if you remember earlier, we said that the only quantity that links all 6 of these graphs, or all 6 of these component output values, these function values, is time. And so right now we're trying to relate x from here with y from here. And the only thing that links these two things together is time. So we really need to take that question and back it up so that it's in terms of time. So we're going to take a look at the y max as being this y value, but the time that it corresponds with is the 5 over 2. So another way of saying this is to solve for x when time is equal to 5 over 2. And therefore x at 5 over 2, well, we know that time 5 over 2 corresponds with the point B, and we happen to already label point B on that x graph. So the answer we're looking for is the 125 root 3 all over 2. And the units for x is in meters. In fact, it's not a bad idea to give the units for each of these axes. We have meters for both the x and the y position components. We have meters per second for the velocity components. And we have meters per second squared for each of the acceleration components. Okay, moving on to the next question. How far away horizontally from launching did the object land? How far away sounds like distance. And in this case, we solve for distance. Well, it's horizontal distance. We should be really clear about that. Solve for horizontal distance such that the object lands. So when we want to rewrite this, we know that object landing corresponds with y equal to 0, and y equal to 0 corresponds with point C, which means t is equal to 6. Now, solving for the horizontal distance, we want to know in 2 dimensions, if we were to draw this motion or this path of the particle in y measured in meters versus x measured in meters, we know that the object starts at a height of 30 meters at the horizontal position away from you, doing the launching of 0, and goes to a final position of, if we put point C here, 6 comma, if I substitute 6 into this equation, I'm going to get 250 times 6, 25 times 6 is 150 root 3. Okay, what am I doing here is I'm saying that the initial point is at 0 comma 30, and then the final point is at 150 root 3 comma 6. And so, comma 0 for the height. And so we're going to get some parabola with the points A, B, and C, but here the A is at 0 comma 30, the B is going to be located at 125 root 3 over 2, comma 245 over 4. And then the point C is going to be at this x and y coordinate here, which is 150 root 3, comma 0. And so what we're finding here is we're asked, the horizontal distance is really just the distance from here to here. And so we know that the initial, there's no change in direction, so the position, the final position is the same as the distance here. So we just want the horizontal distance between points A and C. And so that's going to give us 150 root 3 minus 0 meters is 150 root 3 meters. The next question is a question of speed, and if we recall our definition about speed, it is the magnitude of the velocity vector. And we specifically want the speed at 5 seconds, so we want the magnitude of the velocity of 5 vector. So the velocity vector is given by an x component and a y component, and we can work out the velocity of 5. I'll do it over underneath here. The velocity at time 5 is given by so many I hats and so many j hats. And so we can go to the x component of velocity, which is 25 root 3. It's a constant. So even at time 5 seconds, that velocity component doesn't change. So we put 25 root 3 in here. And to get the y component, we go to the y component graph and we substitute 5 in and we work that value out, given by the formula. Negative 10 times 5 is negative 50, plus 25 is going to give us negative 25. And so we have our velocity vector has two constant components at an instant of time. Therefore, our speed is going to be given, the magnitude is going to be given by Pythagorean theorem, namely 25 root 3 squared plus negative 25 all squared, and then square rooted. But maybe these numbers look familiar, particularly if you factor out the 25. This looks like a vector with positive x and negative y components in quadrant 4. It's going to go a little wider than it is down. And this vector here is actually a similar triangle with a parent vector, which has a reference angle of 30 degrees. So if we know our parent vector of 30 degrees, a parent triangle, hypotenuse of 2, opposite of 1, and adjacent of root 3, we can see that the red velocity of 5 vector is actually a scaling of that vector. Namely, this is 25 root 3, the y component is negative 25, and just by using similarity and scaling, we can see, technically this is a negative 1 here, we can see we have a scale factor for all sides of this triangle of 25. What that does for us is allows us to multiply 2 times 25 to get the hypotenuse of this triangle or vector to be 50. And so instead of having to work out all of this calculation, we can get 50 meters per second as the speed at 5 seconds. In part H, we are asked for the total vertical distance traveled by the object. And so in much the same way that we talked about the horizontal distance, we need to consider the distance between 2 points. Now, if we take a look at the object is going up and then the object is going down. And so we are going to have a vertical displacement from points A to B, which is positive, and we are going to have a vertical displacement from points B to C, which is negative. And so we really need to break up the motion to every point where the particle turns around when we're calculating the distance. So here, when we want the total distance, I'm not going to write vertical, it's going to be implied. The distance total is going to be the distance up plus the distance down. And the distance up is actually going to be the absolute value of the displacement up added to the distance down, which is the absolute value of the displacement, delta y, from points B to C. And so from here, we can work out y final minus y initial plus y final minus y initial. And you can substitute these heights in directly because we have them all listed in the graph. We know that the height at A is 30, then 245 over 4, and then 0. So we can substitute all of those in and simplify. So we get 254 over 4 minus 30 plus 0 minus 254 over 4. And finishing that off over here, we get for part H that the distance, the vertical distance total is going to equal 2 245s over 4, which is 245 over 2, minus 30, which is 60 over 2, for a total of 185 over 2 meters. Then the question is asking what is the displacement, which is a vector, from beginning to end of launch. So we want to calculate the displacement vector, keeping in mind that displacement is the change in position. We want the change in position from the end of the launch, so from time 0, the beginning to the end. And so we do position final minus position initial. We have the position vectors because we have all of the components. You can use the vector format here in the green if you want. We just simply don't use this expression. So we've got 25 root 3 t I hats, and then this quadratic function times j hat. What we're really doing then is looking for this position function in the xy plane. I said position function, I really mean this vector, and this is the displacement vector delta r from point A to point C. So we're trying to find the vector. One of the misconceptions when we read questions like this is that we assume that we're coming up with a scalar quantity, but it doesn't ask for the magnitude of the displacement. And therefore, we are well within our rights to simply leave our vector as an expression in terms of I hats and j hats. So I am going to write, I'm not going to use I hats and j hats right now. I'm going to write my R6 vector, which is going to be 150 root 3 comma 0. And then I'm going to subtract my initial position vector, which is 125, oh sorry, it's going to be, this is 0, 0, isn't it? It's going to be my 0 for my x and my 30 for my y, same as these values over here. So I have 0 comma 30, and I'm going to end up with the position vector of 150 root 3 I hats minus 30 j hats. Now, of course, if the question did say to come up with the magnitude of displacement, you could find the magnitude of this vector, which would be the length of the vector up here, by using Pythagorean theorem. And then in part J, we are asked to find the horizontal position. So no longer are we asked for a vector, we're asked for a component. So we want to solve for x again. Now keep in mind that x is the same as r subscript x. We've just abbreviated it because this is what we've been using all along in Cartesian regular algebra and pre-calculus. So we're finding the horizontal position. We're solving for x such that, now it says the word when, but it says the vertical component of velocity, and that's just a lot of words to say v subscript y is equal to negative 25. So recall again that all of these components, rx, vx, ry, vy, etc., have one thing in common, and the thing that they have in common is time. And what we're really looking at here is to come up with a relationship between Rx, or simply x, and Vy. And so the one quantity that relates these things is time. So we're really trying to pinpoint it probably back to one of these special points, A, B, C, but maybe it's relating it to some other time. And that's really the key of this question. You have to find the time first. So we take our expression for Vy, which is negative 10t plus 25, and substitute it for Vy. Negative 10t plus 25 equals negative 25, which implies, if we solve this quickly, negative 10t equals negative 50, and t equals 5. Now it's a good thing that t equals 5 instead of negative 5, because it wouldn't make sense for the time values to be outside of 0 to 6, especially when Vy does equal negative 25. If we look here, the Vy value of negative 25 corresponds with the time value of 5, and that's the 5 value that we're asked to plug into our Rx component equation. So substituting that t equal to 5 into the Rx component equation gives us that Rx of 5, or x of 5, is equal to 25 root 3 multiplied by the time value of 5, which gives us 125 root 3, and the units will be in meters. We can correspond that on the graph, and if the number 125 root 3 were meaningful to us, we'd be able to see that it makes sense. At least we can still confirm somewhat graphically that it seems reasonable, especially if we approximate these radical numbers with a calculator. The last question then says to write an equation for the vertical position as a function of the horizontal position. What we're really asking to do now is to eliminate the time values and come up with a y versus x Cartesian equation. So we have some equations right now for x and for y, namely the x and y position component equations. So I can call it Rx or simply x. And I can call the second one Ry or simply y, which is the quadratic. And so we are trying to eliminate t because we don't want time to show up any longer in this equation. So this pair of equations for x, y, and t is known as parametric equations. And when we eliminate t, we get the Cartesian equation, which is what really we're asked for in this problem. So the Cartesian equation has the time eliminated. So we're going to solve for t in the first equation because it's easier to solve from the linear equation because time shows up only once, as opposed to in the quadratic, time shows up twice. So we get that t is equal to x divided by 25 root 3, and when we substitute that value for t into the second equation, we get that y is equal to negative 5 times x over 25 root 3 all squared, plus 25 times x over 25 root 3 plus 30. And therefore we can come up with a single Cartesian equation that y is equal to negative 5 over 25 squared over root 3 all squared. So that's going to be 5 to the 1. This is 5 squared. All squared becomes 5 to the 4, and that's times 3. So it's going to be 5 to the 3 times 3 in the bottom, so it's going to be 1 over 3 times 125 times x cubed, and that's a negative overall. Then plus 25, and 25 reduced, so plus 1 over root. I just noticed that I wrote x cubed here. This is x squared. This is going to be 1 over root 3 times x, and then plus 30. And that's going to be the equation of the parabola if you were to watch a path of blinking lights for, say, a ball tossed in the air. That's the path measured in meters vertically and meters horizontally. A lot of people think that this has to be measured in seconds, but we're not confusing this graph with this graph. Namely, this is a graph of y measured in meters versus time measured in seconds, where this is 6 seconds along the axis. This is 125, I think it's let's see what it is, 150 root 3 meters. And so the scales are different because x does not equal to t. X is equal to this velocity value, this something measured in meters per second, multiplied by time measured in seconds to give us the x measured in meters. So there you have it, quite a detailed analysis of projectile motion using the rule of 4, using the graphs, the equations, and relating everything back so we can see what we're talking about. Thanks for checking out Raylene Math.